We're going to start a new chapter today, chapter 9, Sinusoidal Steady State Analysis. Okay, so far we have been looking at DC sources. Sources, the voltage or the current sources, whose value was not a function of time, it was a constant value, 5 volts, 3 amperes, so on and so forth. Whatever its value was, it was constant. Okay, if you were to plot the DC value as a function of time for the voltage source, you pretty much see a straight line, a horizontal line. Now, we are going to look at a new class of inputs, the kinds of inputs that are time varying, okay? And a very good representative waveform for our time varying inputs is a sinusoid. We are mostly interested in cosine and sine, okay? And if I am to plot the voltage value of this guy with respect to sine, with respect to time, it would be a sinusoidally varying waveform. It could be cosine or it could be sine. Okay, so that's the idea. How does my circuit behave or respond when it is subjected to a time varying input? Okay, as a running example, as a stand-in for time varying inputs, we see uh, the use of sinusoid. Okay, as a running example of time varying. So this chapter introduces the idea of time varying voltages and currents, something we did not discuss so far. And one particularly useful time varying signal is a sinusoidal wave. Okay, so we'll use complex numbers, and this is something that we're going to introduce in this topic. How can you use complex numbers? 5 plus j4 or 3 plus j4, a number that has both a real part and an imaginary part. Okay, I'm also going to show you the idea of phasor, okay, where it's a useful notation to represent sinusoids and the response of different circuit elements when subjected to sinusoids. Okay, typically the form is going to be magnitude times some phase angle. Okay, and we'll talk about that shortly. So two new ways. So far we have only been using numbers, real numbers, 5 volts, 250 ohms, 1.6 milliamperes, so on and so forth. We have been using real numbers to represent the circuit conditions. Here on out, we'll also be making use of imaginary numbers, complex numbers, okay? And of course, phasors, okay? So first, let's look at the sinusoid source. A sinusoid voltage produces a sinusoid source produces a voltage that varies sinusoidally, okay? It could be shown here is a cosine, okay? The idea that the wave is maximum, it begins at 0 or close to 0, that represents a cos wave, okay, a cosine wave. If I were to do this, that would be a sine wave, that would be a sinusoid, right? Let's see. This would be a sinusoid without any phase. Okay, just with some frequency and phase value equals to 0. Okay, phase meaning, the meaning of phase is what's the value or the offset of the wave. Okay, typically you would expect the cosine wave to be beginning at when the at time 0, you would expect that to begin falling from 1. Cosine 0 is 1, right? So, but if you, as you can see, the blue wave is offset. Okay, the blue wave is offset by certain amount. Okay, like so. It's offset by some time at the origin, at the 0 time. Okay, when the time is 0, it's offset by a certain amount, and that represents the phase. Okay, what's the value? What's the offset?
So
Okay,
would that offset
at
be
origin?
phase shifting, like a phase shift?
Yes, the offset. The offset is expressed in terms of phase shift.
Okay.
Okay. So the period of the sinusoid, so it can be quantified, the offset can be quantified in terms of the phase. So let me write it here. This guy represents the offset. Okay. The period of the sinusoid function is t. Okay, this guy, the time between two peaks is t, and therefore 1 over t is the frequency. And what we typically do is we like to express the frequency in angular frequency as opposed to hertz. So we can use omega is 2 pi times the frequency in hertz. Okay, and the units for omega would be radians per second. Okay, the units of frequency would be number of cycles per second or hertz. Okay, so this guy, the purple guy on the top, represents a cosine with phase 0. Okay, if I were to shift it, offset it, then I would have a new cosine wave with a phase shift. Okay. Okay. Now, let's see. If I have a cosine wave that looks like this, V is Vm cos omega t plus phi. Let's see, did we see something like, yes, right here, we saw this, right? There's an amplitude component to it. The phase angle determines the value of the sinusoid at t equals to 0. Okay, that the value at time equals to 0 is represented by the phase angle. Okay, for example, if we let the phase angle to be 90, then what happens is when you plug in okay, a value of 90 into the phase, you see that the output is 0 volts. Okay, so this cosine wave that's supposed to begin at 1 is offset by 90 degrees now. Okay, now we usually report the phase angle in degrees for readability. Okay, but we can also express it in radians. Okay, pi by 180 x radians. Okay, what you want to remember is 360 degrees corresponds to 2 pi radians. Okay, 360 degrees corresponds to 2 pi radians. Okay, 1 degree is 2 pi over 360. Okay, and then we can use this relation to find the number of radians that correspond to a degree. Okay, now let's look at an example. So this guy, the Vm here, represents the amplitude, okay, the maximum value. A sinusoidal current. So when I say a sinusoidal current in this class, I mean Vm cos omega t plus phi, unless specified otherwise. Okay, in this class, we're going to deal in terms of cosines. There's no necessity that we have to confine ourselves to cosine. We might as well have used a sine wave, but the textbook sets the note. That's the wave to be cosine. Okay, so a sinusoidal current has a maximum amplitude Vm of 20 amperes. The current source. The period is given to be this guy. The t is given to be 1 millisecond. Okay. What is the magnitude of current at t equals to 0 is given. That is given to be 10 amperes. So you should understand that this information corresponds to phi. Okay, this information corresponds to phase. This information is amplitude, frequency. This information is phase. Okay, so what we can do is there are a bunch of questions. What's the frequency of the current? The frequency of the current is simply, we can express it in 1 over t. The answer to that would be 1 over t, or 1000 hertz. Or if you were to express it in radians, that will be 2 pi radians per second. Okay, so frequency is simply 1 over the time period given, which is 1 millisecond. That's the value given. And therefore, I have frequency equals to 1000 hertz. Okay, now am I ready to write the expression for I of t? Okay, I of t. Now, Im value is given. So excuse me for this. So this is not voltage M, this is Im, the amplitude. Okay, because it's a current source. So this guy, Im, represents the amplitude for the current source. I have that. I have the value of omega to be 2000 pi, right? So 1000 hertz corresponds to 2000 pi. So when I have frequency to be 1000 hertz, my omega is going to be 2 pi f. So 2 times pi times 1000, so that's 2000 pi. Phase angle. Okay, phase angle is not directly given, but some information that could lead me to phase angle is given. Okay, how do we find phase? So we have just about everything. We have the Im value, we have the omega value, and then the only thing that's missing is phi. In order to phi, we use the given equation that I value at t equals to 0, the value of that is given to be 20, right? Or is it given to be 10? The value of I at time t equals to 0 is given to be 10. So I could use that relationship. I could plug in t equals to 0 into this. So all of this goes away. 20 cos phi comes out to be 10 amperes. Okay, all of this goes away because I'm plugging in t equals to 0. Okay, so I'm left with 20 times cos phi, meaning that cos phi is 1/2 and phi is cosine inverse of 1/2, which is 60 degrees. So that gives me the value for phi. So now I have the frequency, I have the amplitude, and I have the phase. I should be able to write the expression for I of t. Does that make sense? Questions, please.
It does make sense. And my only question is the offset term.
Okay.
Is that the same as like frequency error? If say I had some sort of frequency source that was supposed to be emitting 1,000 hertz, but I measure it to be 990 hertz, would the difference there be the offset or error?
The offset is coming from phase. Okay. I'll give you an example. Why don't I talk about the exact same wave that we are looking at right now? Okay, which is cosine. Let's see, what's the best way for me to, okay. So cosine 2000 pi 20 times t. Okay, let's take a cosine wave which has no offset. If I were to plot it, it would appear something like this. Right? So pardon my, I'm not the best artist in the world. So at time t equals to 0, so along the x-axis is time, along the y-axis is the current. Okay, at time t equals to 0, the value of the cosine wave and the current source is going to be 20. Okay, and then at time t that corresponds to a phase of pi by 2, or let's say 1/4 of a sine of a time period. Okay, when you look at 1/4 of or a half of a time period, okay, then so this guy is your time period, right? That value is your time period. It's time this guy to be black. Okay, this guy is your time period. Half of that is from positive peak to negative peak. This guy is time period over 2, and then positive to negative, or positive to 0, that's going to be 1/4 time, 1/4 your time period, right? So this is your cosine wave without any phase, correct?
Yes.
Now imagine that this cosine wave is shifted, okay, by 1/4 time period. Style this. Now I'm going to, okay, let's see. All right, so this new sine wave there's no error in the frequency. If you were to measure the frequency of this guy, okay, the frequency of this guy, which is 1/t, is exactly the same as the frequency of this guy, of the red wave, right?
Right.
So they're just time shifted. One is just the time shifted version of the other, okay? And that represents a cosine wave with some kind of phase shift.
Okay, perfect. Thank you.
Okay, so phase shift does not correspond to any change in frequency. It only corresponds to the time shift, okay, how it is shifted left and right.
Perfect. Thank you.
Okay. Sorry if I failed to make things clear. If I only made them more murky, my bad. But one way to think about phase shift is to see if it is moving left or right. Okay,
Perfect.
let me do this one more. Let me make another attempt to do this. Okay, duplicate this. So let's say I have a a wave. Let's simply repeating in this fashion. Okay. If I were to shift it by 90 degrees, okay, if I were to shift it in time and then just move it to one side, okay, to the right or to the left, just so it's offset when the peak of the red wave happens, the bottom peak, the blue is experiencing a top peak. So something like this. When I do that, what happens is it's offset. It's offset by about 180 degrees out of phase. Okay, it's offset by 180 degrees out of phase. Okay,
So it's
that's all there is to the idea. Say that again.
I said, so it's just inverted then in that case.
In this case, it's inverted, which corresponds to a phase of 180 degrees.
Okay. That makes a
Or
lot more
pi
sense.
radians. Okay.
Yeah.
So if you compare the frequencies of both of these waves, they're still the same. Okay, that's the idea. Phase shift does not change the frequency. Now, the phi can be calculated by plugging in t into, so by t equals to 0 into that expression, and it will give me a value phi, which would have given a value of 1/2 at the origin, at the time t equals to 0. Okay, so that's all there is to it. Okay, now, so the argument of phase shift is that if I move the wave to the left or to the right, it's still the exact same wave with the exact same frequency and amplitude, except that it's delayed. Okay, now a sinusoid has a 0 average value. Okay, if we were to average the area under the curve, okay, if we were to if we try to find the continuous sum and average it over time, that's what an integral is, right? It's a continuous sum. Then the positive cycle, the positive half wave cancels the negative half wave. Okay, if we were to simply average, so now I have to have a different metric. Okay, a different metric that provides some kind of a sense of an average. Okay, not exactly an average, because a simple average is 0 and it's not insightful. So what we do is we define this root mean squared term. Okay, root mean squared term, and we typically do this for any data that is spread that has a positive and negative values. Okay, when you try to look at the average of positive and negative values that are equally spread out, you may come up with a mean or an average that's close to 0. So statistically, if you want to find some equivalent to mean that is not 0 but a bit more insightful than 0, to understand positive and negatively spread terms, we define root mean squared, where we squared the wave of interest to me or the input of interest to me and add them. Okay, find the sum of the squares and divide that by time, and then find the square root of that. Okay, we can find the Vrms value of a sine wave to be Vm over root 2. If I have a cosine wave that looks Vm cos omega t plus phi, the RMS value for this guy is going to be the peak value over root 2. Okay? It's a integration formula. We have to do a little bit of a rearrangement here. Cos squared theta is 1/2 plus cos 2 theta over 2. That's the identity we use here. Okay, so I'm going to replace this guy, all of that guy, with this identity. Then it's easy to see how this 1 over 2 gives me, when I integrate it, t over 2, and when I integrate cos 2 theta over 2, I'm left with 1 over 4 sine 2 theta by the derivative of that guy. Okay. Now, so once I do that, I should be left with a RMS value of Vm over root 2. That's the root mean squared. Okay, that's in some sense represents an average. Okay, not a simple average, but a bit more a squared root mean squared average. Now find the RMS value of a sinusoid with a DC offset. So that's something we did not do so far, right? We only looked at RMS value with no DC offset. It's purely cosine wave or a sine wave. Now we have a cosine wave that is sitting on top of 5 volts DC. Okay, so what this says is, okay, let's say if I did not have this value, if I simply had cosine 2 omega t, then the wave would look something like this. Okay, the wave would look, that's terrible. Okay, the wave would look something like that, a cosine wave. Now, if I have a DC offset, this guy, what it does is it provides a DC value 5 volts on top of which this cosine wave is riding. Okay. Okay. If you were to plot the overall V of t, it would appear something, the sum of the two, the DC and this guy. Okay, what the DC offset has simply done is to move the wave up and down. Okay, so to move the wave left and right, we use the phase angle. To move the wave up and down, we simply apply a DC offset value. So what is the root mean squared of a sinusoid that has a DC offset value? Well, we could do the exact same thing, 5 plus 2 cos omega t whole squared, and integrate that and divide it by the time period 2 pi. Okay. So this guy is cos omega t. This guy is 5 plus 2 times cosine omega t. Okay, so that's the calculation of root mean squared value. All of that goes to 0 because you're integrating a cosine wave over all of its one full wave. Then we can find the VRMS. We can continue the calculation. Simply 25 plus 4 cos squared omega t. And then I can do the integration and then the square root and find that this guy is VDC squared plus VRMS squared over 2. So it's simply VDC squared plus V squared M over 2, all of that under root. Okay, so earlier I had just this term, Vm squared over 2, all of that under root. When I have a DC value, the RMS is simply going to add the square root of DC inside the square root. Okay, that's the VRMS with a DC offset.
Now, sir,
Okay?
is that formula true always as far as
Yes,
different sinusoidal? Okay,
as far as a DC offset to a sinusoid wave is concerned.
thank you. I just wanted to make sure that formula wasn't specifically for that question or something.
No, it is not. You can apply this to any sinusoid with DC offset.
Perfect, thank you.
So that's the sinusoid wave. Let's look at the sinusoid response. Okay, when we input any signal into a circuit, we expect to see an initial response, and then after a long time, the response that persists. So if I have a circuit and subject it, the output of a circuit in response to some kind of input, okay, what is going to happen is there are two parts of the response or the output. So when I say response, I mean output. It can be transient, it could be steady state. Okay, so the idea is there is an initial knee-jerk reaction that the circuit shows to any kind of input. That's called the transient. But if you wait long enough, if you continue to apply the same input and wait long enough, it's going to settle into some kind of rhythm, a steady state response, a more steady state response. That's called the steady state response. So there are two parts. There are two ways in which a circuit responds to sinusoid signals or any kind of time varying signals. Okay, the initial knee-jerk quick reaction, the immediate response. Okay, initial immediate response, which is called the transient response, and if you continue to apply the input, then the output settles into some kind of a steady state output. Okay, so the total response is equals to the sum of the transient or the combination of transient and steady state responses. Okay. So for a linear circuit, these are the circuits that we talk about in this class. When I apply a sinusoid input, so these are important characteristics that are handy when I want to solve problems in this class. Okay, when I take a linear circuit and apply an input that is sinusoid, it's pretty much guaranteed the output is also going to be sinusoid. Okay, not only is the output going to be sinusoid, the frequency of the input and the frequency of the output are the same. Frequency of input is the frequency of the output. Okay, similarly, the amplitude of the input. So let's say the amplitude of the input is Vm input. Okay, let's say the amplitude of the output is Vm output. Okay, there's no guarantee, and as a matter of fact, you should almost always expect that V in, VM input will not be the same as VM output. Okay, so if your input is like so, the output may be an amplified version. Okay, the output may be, if that's your input, the output may be an amplified version, but with the same frequency. Don't forget that it has the same frequency still. Okay, therefore, the frequency is still the same, but it may be shifted. The output may be shifted. Okay, for, in time. Okay, so the phase may be different. Okay, so if you were to look at the phase of the input and the phase of the output, there's no necessity that phase of the input will be the same as the phase of the output. Okay, more likely than not, it will not be the same. Okay, the phase of the input is going to be different from the phase of the output. Okay, so the idea is when I take a linear circuit, okay, what changes is VM, or the amplitude, and the phase, and what does not change between the input and output is this guy, the frequency. Okay, the frequency does not change between input and output when the circuit is linear. Okay, so it would be a good idea for us. So if I were to take a linear circuit and apply a sinusoid with some amplitude, with some frequency, and some phase, okay, the output is going to be some other amplitude, the same frequency, but some other phase. Okay, so I need to be able to understand the relationship between VM input and the phase input versus VM output and phase of the output. Okay, so this representation is called phasor. Okay, some kind of representation of the input amplitude and phase so that you can compare it to the output amplitude and phase. Okay, that's all there is to the idea of phasor. Okay, phasor and Laplace domain, that is not covered in this course. They're the representation of circuit in the most common way to mathematically describe it. Just so I can manipulate it, I can understand the behavior of circuit and mathematically get a handle around it. Okay, we define what a phasor is. Okay, phasor is a complex number that carries the amplitude and phase angle information about a sinusoid function. So I just defined a phasor for you. Okay, if I have a sine wave that looks like this, okay, Vm cosine, I don't know, 2000 pi t plus phi n. Okay, that's the input. Then let's say this guy is phasor is nothing but Vm comma input. Phasor is nothing but when you take the amplitude and the phase and represent that together, that's all there is to the idea of a phasor. Okay, so phasor is the complex number that carries the amplitude information and phase angle information. Okay, we can start with Euler's identity that e to the j theta plus or minus is cos theta plus j sine theta. Okay, so here is the notion of a complex number. E to the plus or minus j theta is cos theta plus j times sine theta. Okay, if there is an amplitude associated with it, A, then A times e to the plus or minus j theta is A times cos theta, and j, so this part is called the real part, and here is the imaginary part. Here is the imaginary part of the complex number. Okay, now we can see that the authors in the textbook show that we can let the magnitude, okay, and phase angle be represented by the polar form, represented in the polar form, okay, Vm e to the j theta as the phasor form of Vm and cos omega t. If I have a wave, sinusoid wave, and I want to represent it in a more concise manner, I take the amplitude and the phase, okay, and represent them in one notation together. That is called, that's represented by a phasor, okay. The frequency component is represented by e to the j omega t. E to the j omega t represents the frequency component, but I'm not too worried about the frequency component because that's not changing between input and output, okay. The input and output have the exact same frequency components. So if I understand how the amplitude and phase are changing between the input and output, that's a good way for me to understand the response or the behavior of the circuit in response to the input. Okay. So the phasor's trigonometric form of magnitude and phase angle is given to be something like this. Okay. If I have Vm cos phi plus j omega pi, it's represented as Vm e to the j phi, which is the phasor form of Vm angle phi. Okay, so Vm, we'll ask that you accept this representation. So what you simply have to understand is this amplitude is this guy, and the phase, okay, the phase is that representation of a phasor. Okay, so let's look at the passive elements: resistor, capacitor, and inductor in the frequency domain. So far, we have been applying DC voltages to them. Let's see how they respond when we apply time varying signals as inputs to them. Okay. Since we have signals that change with time, and where that change is described in terms of frequency, we now need to represent circuit elements in frequency domain. Okay, so we have V IR relationship. Okay, so when you look for the relationship between voltage, current, and resistance in the frequency domain or in a time varying input. So what happens is this is V, okay, this guy is I. The current here is a time varying signal, that's I, and then this guy is resistance R. Okay, so as you can see, V is R times I am cos omega t plus theta I. Okay, this represents the time varying component of my current. Okay, the phasor form is given in terms of V and I are shown as phasors. Okay, the PowerPoint shows them in boldface font. Okay, the bold V and bold I are the phasors. If I were to express this guy in phasor form, okay, R times Im, okay, and then e to the j theta I, e to the j theta I. Okay, now R IM angle theta I. Angle, it should really be theta I, right? Angle theta I. So that's the amplitude, that's this guy. And then there is the phase component, which is this guy, okay? Which is the phasor representation, okay? This, let's see, something in the chat. Okay, so the idea is that this guy is the polar form of the current. Okay, this guy is the polar form of the current. So it's simply a representation of the sinusoidal current source. Sinusoidal current source. Okay, we still have the relationship V is IR. Okay, V is IR. There is no phase shift between the voltage and current in the resistance. Okay, that's something we want to understand. When we apply a sinusoidal wave to a resistance, okay, the output is also sinusoid wave with the exact same phase. Okay, the phase is exactly the same. There's no change in the phase angle. Okay, now let's look at the relationship, VI relationship for an inductor. Okay, you know, if we assume the current is a time varying component here, okay, we know voltage is L di by dt in an inductance. Okay, voltage is L di by dt in an inductor. So L d by dt of this I. Okay, this is I because that's L di by dt. Then what I get is the derivative of cosine wave is negative of the sine wave, and of course the chain rule gives me a product of negative omega. So what we have seen is the voltage in an inductor is negative omega L Im sine omega t plus theta I. Okay, so if I were to put it all in terms of cosine wave, the output voltage, V output, is negative omega L Im cosine omega t plus theta I minus 90 degrees. Okay, so this is the expression for voltage when I apply an input that has this form. Okay, so what you can see is that this guy, when you express it in its phasor form, okay, when you express it in its phasor form, let's see. Okay, this guy becomes the amplitude, okay, and then all of this becomes the phase. Okay, all of that becomes the phase. Okay, that's the phasor representation of it, right? I only take into account the phase shown in green and the amplitude shown in purple. Okay, now we know e to the negative j 90 degrees is really negative j. Okay, so what we can do is we can represent this guy, we can replace this guy to be negative j. Okay, that guy is going to be negative j. So all there is to it is that V takes the form of j omega L times I e to the j theta I. Okay, so if I think of this as some term z, okay, if I think of this as some term zl, okay, and this term is still going to be, what is this term over here? That's still exactly the input that I'm applying, right? That's the input that I'm applying. If I were to express the input in, so I am angle theta I is the input current, okay? So I am angle theta. So what we can see is the output voltage of an inductance is Z times ZL times the current in the inductance, where ZL is given by j omega L. So if I were to replace this inductor in a frequency domain, so this inductance has, inductor has an inductance of L, then in frequency domain, it behaves similar in some sense to a resistance with impedance value equals to j omega L. Okay, so j omega L is the frequency domain impedance. Okay, we call this as impedance. Okay, we'll come back and talk about it. Okay, now back to the phasor voltage of the inductor, we can simply say that omega L angle 90, IM angle phi. This guy is 90 degrees. Okay, and then there is an additional phase shift. Okay, so the voltage across an inductor, leads the current through the inductor by 90 degrees. Okay, I'm going to give you a mnemonic to remember how the voltage in an inductor relates to the current. Okay, in an inductance. That's something we want to look at. So Eli the Iceman is a statement that I use as a mnemonic to remember the relationship between voltage E in an inductor leads the current by 90 degrees, whereas the current in a capacitor leads the voltage by 90 degrees. Okay, that's something we want to, Eli the Iceman is something we want to use as a mnemonic to understand, to remember the relationship between the voltage and the current. Okay, so if you think about it, the current is this guy. That's the one shown in green is the current, right? Okay, the voltage on the other hand has a phase angle of 90 degrees, omega L, 90 degrees. Okay, therefore the voltage leads the current by 90 degrees. Voltage in an inductor, Eli, leads the current. E leads current. Okay, so the last result shows that the voltage across an inductor leads the current by 90 degrees. Okay, we like to, power engineers, on the other hand, like to say that current lags the voltage in an inductor. Okay, both of these are valid ways of saying. For now, all we have to understand is the voltage leads the current in an inductor. Okay, we can understand the relationship between the voltage and current in a capacitance. Okay, so what you will see is that the voltage, so V is I times R. When we saw for a resistance, V is j omega L times I in an inductor. In a capacitance, V is 1 over j omega C times I. Okay, so the idea you want to remember is when you convert a resistance to a time domain, into a frequency domain, its resistance value, the relationship is still the same. Okay, when you convert an inductor into frequency domain, what you'll see, there is a ZL, there is a component. If you call this component as ZL, okay, then this equation is pretty much going to appear like V equals to ZL times I. So in some sense, it behaves like a resistance because there is V is IR, where Z is called the impedance in an inductor. In a capacitance, V equals to ZC times I, where ZC is 1 over j omega C. So the argument I'm going to make is when I convert the voltage source, when I convert the inductance and capacitance into frequency domain, I get what is known as impedance. Impedance. Okay, so let's look at an example if we can. So here, okay, the frequency domain, construct the frequency domain equivalent of the following circuit. Okay, so I have a circuit in time domain with its ohms given, with its L given, with its capacitance given. Okay, so let's see what is given. I'm given the value of this resistance, 10 ohms. I'm given the inductance of this guy, L. I'm given the C, the capacitance of this guy. Also, I need this value, that's the omega, right? That's the omega frequency. Okay, that's 2 pi, actually, that's the frequency, and I need to convert it to omega. Okay, I need to convert it to ZL. Now, what you can see is if I am converting this circuit to frequency domain, then the resistance is not going to change. The resistance will still be the same. This resistance will also be the same. Now this inductance, okay, I'm going to find the ZL of this guy, the ZL of this inductance, okay, which is J times omega L. Omega is given to be 2 into 10 to the 5. That's J, that's omega. And this guy is L. So when I convert this inductor to the frequency domain, I'm going to be left with this guy, J8 omega. Okay, then I can convert this capacitance. Okay, I can convert this cap into the frequency domain by finding 1 over j omega c. Okay, remember 1 over j omega c, that's the relationship between V and I in a capacitance. And this guy is the VI relationship with an inductance in frequency domain. And this guy is the resistance. Okay, so I can calculate this frequency dependent impedance term. Okay, that's what I'm doing here. ZC is negative J over omega C, where negative J. So what I have done is simply multiply the numerator and the denominator by J. Therefore, J squared is negative 1. J squared is negative 1. Okay, that's the relation that I plug in here. Okay, so what we have done is to calculate ZC, ZL for this guy. Now what I can write is when I convert this circuit into frequency domain, the resistance remains unchanged. Okay, this resistance remains unchanged, and this 40 microhenry or 40 millihenry, 40 microhenry is converted to complex impedance J8 omega. Okay, similarly, this 1 microfarad capacitance right here is converted to 1 microfarad capacitance is converted to negative J5. Now what I can do is to simply add them like they were resistances. Okay, so in order to do that, what I do is to calculate the inverse of all of this. Okay, let me call YR the admittance of a resistance to be the inverse of this guy. Okay, I'm simply calculating the inverse of YR. What's the sum of these two? Okay, the sum of these two is RL plus ZL. Okay, and when I calculate the inverse of that, I get the admittance of that branch. Okay, and then if you look at the impedance of this guy, that corresponds to ZC, and then 1 over that corresponds to the impedance of this guy, admittance of this guy. So why am I doing this? Okay, if you notice, this all of this circuit is simply a parallel combination of three branches. There are three parallel branches. Okay, if I had a circuit that looked like this with three parallel resistances, how would I find the equivalent resistance if this is R1, R2, and R3? The equivalent resistance 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So the reciprocal of resistance of each of these branches, okay, I would add and then invert it. Okay, so that's exactly what I'm doing here. So the first branch, okay, the first branch is this guy. The reciprocal of that guy corresponds to something like this. Okay, then there is a second branch over here, this guy. Okay, that's exactly what I'm doing, which corresponds to a resistance over here. Okay, the third branch over here is a capacitance. So I find the impedance of that guy, and then invert it, do the reciprocal of it. That's similar to the branch over here. So all I'm doing is I'm calculating the inverse of this branch, inverse of the impedance in this branch, and inverse of the impedance in this branch, because they're all connected in parallel. Okay, now if I add the admittances, okay, the sum of the reciprocals, that is what I'm doing. The admittance is simply the reciprocal. Okay, when I do that, when I calculate the inverse of the admittances, the sum of the admittances or the sum of the reciprocals, I get Y equivalent. Okay, once I have Y equivalent, the inverse of Y equivalent will give me the Z equivalence impedance. Okay, so what I'm doing is pretty much the exact same thing that I would do if I had three branches with resistances. Okay, except that instead of dealing with pure real numbers, I'm now having to deal with imaginary numbers. Take the sum of the reciprocals and then do an inverse of that. That's exactly what I'm doing. Take a sum of the reciprocals and invert it, or do the 1 over that guy, the reciprocal of that guy gives me my equivalent impedance. Okay, so what we will do is we'll come back to looking at the conversion between the Phasor form. These are all real numbers, right? So these are all imaginary numbers. Okay, all of these are imaginary numbers. The admittance of YR is 0.1 ohms because I have 1 over 10 ohms, which gives me 0.1 mho or Siemens. Okay, notice that the symbol for resistance is omega. Okay, the symbol for admittance is the inverted sign of omega, which is mho or Siemens. Okay, so the symbol or the units for admittance is in Siemens. Now, I can do the complex number calculation for this. This guy is R, which is 6 ohms here. So how did I calculate Y in this branch, YRL? So that's 6 ohms plus J8 omega. Okay, the sum, so the sum, they're connected in series, the inductance and the resistance are connected in series. So what we do is to simply add 6 and J8 omega as if they were two resistances connected in series. Okay, that gives me the value for the admittance. 1 over 6 plus J8 omega gives me the value of the admittance in this branch. Okay, so I can simplify that to be using complex number calculation. I can multiply and divide the denominator, multiply and divide by its complex conjugate. 6 plus J8 omega. I'm multiplying and dividing it by 6 minus J8 omega. So I'm left with this guy in the denominator, purely real number in the denominator. And then the complex number is now showing up in the numerator. Okay, so if I evaluate that, the real part is going to come out to be 0.06. The imaginary part is going to come out to be negative 0.08. Similarly, I can do the exact same thing for this branch over here. For this branch, okay, the impedance is 1 over j omega c. 1 over j omega c is the impedance of this guy. And then the reciprocal of that is 1 over ZC, which is the admittance, which comes out to be 1 over negative J5 omega, which is the same as J 0.2 mho. Okay, negative J5 omega is this guy. So now what I have is three values, 1, 2, and 3. I can simply add them all to get the admittance of the overall parallel combination. So I add this guy YR and I add YR plus L. That's something I get from the previous um, step, and YC as well. So all I have done is added the three results, this guy, and this guy. Okay, that's what I'm doing in this step. Okay, then I have 0.1, and this guy is the impedance from the inductance, and that guy is the capacitance. Okay, then what I have is something that looks like this. 0.16 plus J 0.12 mho, not Siemens. Okay, then what I can do is to find the magnitude of this guy, which is the real part squared plus imaginary part squared under root. That's the magnitude of the complex number, and the phase representation of that is tan inverse of imaginary part over the real part. Okay, phase is arctan tangent inverse of imaginary part by the real part. Okay, the magnitude of this guy is real part squared plus imaginary part squared under root is the magnitude. Okay, there are two formulas that I'm using to go back and forth between polar and between and complex number form. Okay, when I have a complex number with a real part and an imaginary part, the magnitude of that guy, which is the square root of real part squared plus imaginary part squared, that gives me my magnitude. The tan inverse of imaginary part by real part gives me the phase. Okay, so what I can do is I can do this guy 1 over 0.2 angle 36.87. And then when you take 1 over when you take the reciprocal of that, you can get 5 angle negative 36.87. Okay, so that's how you would calculate. That's how you would calculate the Z impedance. So Z impedance here, Z equivalent, is the impedance that's the effective impedance, the equivalent impedance, Z equivalent. Okay. Now, if you wanted to find the voltage, V is I times R. So this is or I times Z equivalent. Okay. So this is Z equivalent. Multiply that by I, which is given to be 8 angle 0. So this is what I have. This is all Z equivalent, and this is I. The product of those two, okay, gives me the voltage. Okay, so the time domain representation of this guy simply is 40 cosine 2 into 10 to the 5. This is the frequency that was given to us minus the phase angle that we obtained from this step. Okay, so if you think about it, all we have done is to start with the input. Okay, start with the input amplitude. Let's see, where did that go? Okay, input amplitude 8 ohms. So I'm going to, okay, this is the input amplitude of the current. Okay, and the phase is 0. 8 angle 0 is given to be the input. Okay, then what we did was to eventually arrive at a result. Okay, eventually arrive at a result that has some amplitude for the output voltage and the phase for output voltage. Okay. Then we can find the different branch currents. The branch current in I1, this branch, I1, is simply the voltage that is applied across this resistance, divide that by R. So 40 angle minus 36.87 by 10 ohms is the current through this branch. Current through this branch would be the voltage that is applied. Okay, the voltage that is applied across this branch, which is the same V, divided by the Z of the second branch, or V times the Y of second branch, which is simply the admittance of, or the reciprocal of Z2. Okay, this is the reciprocal of Z2, which is the impedance in this branch. Okay, we calculated that earlier. J plus 6 ohms, that's the resistance, plus J8 omega, that's the impedance. Okay, and then it's a matter of doing the arithmetic for phasor and real number form. Okay, similarly, I can find the current through this branch. Okay, current through that branch is um, the voltage applied across its terminals, which is V, okay, divided by the impedance of this branch. Okay, let's see. So that's what we would find out. Okay, I2 and I3 is simply, see, the voltage that is applied across its terminals divided by the impedance. That will give me I3. Okay, so what I want to do is to come back in the next class and, it's not probably as clear when I show them on PowerPoint. If I'm going to solve this problem step by step on a plain paper, that might actually make a lot more sense. And that is what I plan to do in the next class when we talk about Kirchhoff's laws in the frequency domain. Okay, so we'll do some analysis using complex numbers and phasor relationship. Okay, when we do some examples in the next class, that will make things much more clear. How about we stop here and then come back and continue from this discussion tomorrow?
Sounds good to me.
Perfect.